great-looking pirate, Jim. So please, a warm applause for Jim.
Well, thank you. I'm glad to be here. We are going to be talking today on a topic, the title of this talk is called Why Not? It's about the Y-Combinator, which I'm sure everybody here is intimately familiar with, right? Good, good. Well, then I won't have to do a lot of introduction. This is the opening keynote talk, and there's some rules that one should follow when doing keynote talks. First of all, you probably want to keep this talk non-technical. This is going to be the opening talk of the conference. It's going to set the tone for the rest of the talks coming here, and you want to kind of make it motivating. You want to keep it a very non-technical, a people type of talk. This talk is highly technical. Okay, well, if it's going to be highly technical, then we should probably make it at least relevant to your everyday programming careers. This talk is extremely pointless. There's very little out of this talk you'll be able to take home tomorrow and say, yes, I can use this on the job right away. Well, then, if you're going to be non-relevant, at least provide some good programming examples for people to follow. No, this is going to be the worst Ruby code you've ever seen. The only redeeming factor of this talk, as far as I can tell, is that it's going to be fun. At least it was fun for me, and I hope it's fun for you. Now, this is the part of the talk where I require some audience participation. I need someone with a scientific calculator, with a calculator that can calculate the cosine in radians. You've got one? Okay. Who said that? Katrina. Okay, excellent, excellent. Make sure you put it in radians. I've done this talk several times, and every time it fails is because they're doing it in degrees rather than radians. So what I want you to do is type in a 0, then ask for the cosine of 0. Oh, okay, you got it? Now press the cosine button again, and press it again, and keep doing that for a while. I'll get back to you. An alternate version of this talk could be effectively computable. You probably know this guy, or at least have heard of this fellow, Alan Turing. A video of the Turing machine. Okay, we're going to run this video and I'll let you watch it. What is this particular Turing machine consists of a tape made out of whiteboard material. They have a dry erase pen that's writing numbers, and you can see he wrote 1011, which is 11 in binary. It's going to count. So it counts by first finding the last digit, and if it's a 1, erasing that and carrying it to the next position, making that a 0. Okay, now he's got, there's 12, so he's counting up to 12. And you can look at this. On the right-hand side, you can see a lighted area. There's a camera right above there. So he moves the tape over to the lighted area to read what the digit is. There's the felt tip pen here, and then the eraser head is one over. So he keeps moving the tape back and forth between them. You can see he's counting. Now he's got, okay, that's 14 right there. Counting up, now it's 15. He finds, okay, that's all there is. He finds the last digit. He increments the 1 to a 0. What? What did I ask? Oh, there we go. All right. And so he's incrementing it here, and now it's up to 16. So he just used a Turing machine, a mechanical Turing machine, to count from 11 to 16. That's kind of awesome. I want one of those machines so bad. So that's a Turing machine, and we realize that a Turing machine is incredibly primitive. You can just write, the only memory in a Turing machine is that endless tape. You can access one position of the tape and you can move it one position at a time. But you can write programs on a Turing machine that can effectively calculate any math function that you can think of. Anything that is computable can be computed on a Turing machine. And that's just mind-boggling to think of something that primitive is actually as powerful as Ruby or Java or any of the other languages that we use day by day. Am I on the handheld now? Okay, I'm just on the handheld. Okay. You might have recognized this guy as well. He's not as famous as Turing, but he's done work in his own area. He came up with something called lambda calculus. And if you're familiar with lambda calculus, it is essentially this. This is the entire syntax of a lambda calculus program. The lambda and the period are punctuation marks. The lambda introduces a function. The thing that comes after the lambda is the name of a variable. The dot separates the variable from the body of the lambda function. And then the body can be any other lambda expression, so it's recursively defined. Here, this is a function that returns its argument. So essentially, this is the identity function. Now, there are some rules in lambda calculus. First of all, the only data structure you have, the only type of data you have, is the lambda itself. So you can have lambda functions, and that's the only type in the entire lambda calculus. So here's how we would represent several things. You can see, let's start with 1 here. We can see 1 is a function of 2 arguments, f and x, and it applies the function f to the argument x 1 time, and that's how we represent 1. 2 is represented by applying the function f 2 times. 0, we can see, applies the function f 0 times. So that's how we represent numbers. Down at the bottom, we have a representation of true and false. True and false are both arguments of functions of 2 arguments. True returns the first argument, false returns the second argument. So it's kind of like an if-then-else. Functions are the only data type. There are no numbers, there are no strings, there are nothing else but functions. And as we saw, we can use functions to actually represent things we're interested in, like numbers and strings, and we can actually build data structures out of functions. That's kind of beyond the point of this talk. Lambda binding is the only way to associate values with variables. You have no assignment statements. The only way to associate a value, which has to be some kind of lambda expression, to a variable is through binding it through a function call. And calculation happens primarily through a process called beta reduction. Let me show you how that works. The top here we have a lambda expression consisting of the value for true, the value for 1, and the value for 0. So we're going to go through beta reduction on this to see what we get out of it. So to do a beta reduction, you identify the function, and you copy it down. So we're going to call it with its argument, which is the value of 1. So we copy down the body of that function, which will be lambda y dot x. We'll identify the argument that is being passed in that's going to be assigned to x, and we replace the value of x in the body with the value of the argument, which is 1. So you get the lambda y dot, then in parentheses, lambda x, f of x. So that's the first step in beta reduction. Now let's do it again with this lambda y function. We identify the function, we copy the body down, and then we replace the argument y everywhere in the body. Well, it so happens that y doesn't exist in the body of that function. So the argument is essentially thrown away, and the final result of this is the value for 1, the lambda value for 1. So if we apply true to 1 and 0, we get 1 as the final result. This is lambda calculus. This is all it is. And essentially, it's a big macro processor. This is a big, take a body of a function, replace it with the value textually, and just keep going. And that's all lambda calculus is. Well, it turns out that anything that is effectively computable can be computed via lambda calculus. And this was determined by Church around 1933, 1935. There were a couple papers on this. Now, he and Turing were working on this at the same time, and when they first came up with this effectively computable idea, we weren't sure if the range of things that could be computed by lambda calculus was exactly the same set of functions that could be calculated by a Turing machine. I think it was around 1937 or so they kind of decided it was indeed the same set of functions, which is kind of wild. Turing machines and lambda calculuses are entirely different. A Turing machine is an endless tape with a state machine that runs on it, kind of very similar to the programming we're used to now. Lambda calculus is a big macro processor and nothing else, and yet they can compute the same functions in both languages, and that's pretty wild. So we see the influences of lambda calculus today. We see it in Lisp, we see it in Clojure, we see it in Ruby, and we like it so much we've done it twice. We see it in CoffeeScript, and we see it in JavaScript. All of these languages support a construct that is very, very similar to the lambda function available in lambda calculus. So that's lambda calculus. Just to return to a topic of fixed points here. And Katrina, what number did you end up with in your cosine calculation? Yeah, tell me what number you have. Oh, excellent, excellent. It turns out that if you keep applying cosine to that value over and over and over again, it converges to a value that's approximately 0.739 or thereabouts. It takes about 90 iterations to do this, and it kind of depends upon how accurate your floating point math is, how accurate your cosine is. If you do this in Ruby, you'll find that around 89, 90, you'll start iterating between two values, one that ends in a 1 and one that ends in a 0, but that's because we're only approximating real numbers. This is called a fixed point. A fixed point is a number, or actually any value, that you feed into a function and it returns that same value back. Cosine has a fixed point at 0.739085 blah, blah, blah. Now, lots of functions have fixed points, and this is the definition of fixed point. Take a value, run it through a function, and get the same value out as you put in. That is a fixed point of that particular function. Now, cosine has a fixed point at 0.739. Sine has an easy fixed point at 0. It would not have been nearly so much fun to calculate the fixed point of sine. Square root, it turns out, has two fixed points, one at 1 and one at 0. Running both of those numbers through square root gives you the same number back. So square root actually has two fixed points. Some functions have no fixed points. The function that adds 1 to its input does not have a fixed point because it's always going to return a different number. But some functions do have fixed points. So keep that in mind. We're going to come back to the idea of fixed points. So now here we get to the demo part, and it's going to be really interesting running this by hand. Tell you what, I will type and I'll pick up the mic and talk. We'll see how that works so you guys can hear me okay. So here is my demo buffer. And let's see, I'm going to run it like this, and this puts stuff up here, and this lambda here is just designed so that the last thing I have in this section here is going to be printed out when I evaluate the buffer, and we can see the answer is going to be 33. So is there any way I can get a mic stand or something if I have to hold this? They're going to look into that. Okay, excellent, because this is going to be really hard. So let's demonstrate a couple things. First thing I want to do is talk about higher order functions. Okay, so we're going to start off by defining just a regular function for you. So here's a function called add1. It takes its input and adds 1 to it. And if we run that on the value of 10, we see we get an 11 out of there. Just for kicks, let's define another function. Cool. Okay, good. All right, now I just have to stand very straight while I type. All right. Okay, very good. There we go. We got multiply by 3. Let's call multiply by 3 onto this right here. And if we add 1 to 10, we'll get 11. If we multiply by 3, we should get our value 33 out of that. And indeed, we do. Excellent. So these are just regular functions. They take a value and they return a new value. Let's write a higher order function. And I'm just using the new Ruby 1.9 syntax for functions. It's cool. I like to call it stabby proc, because you write stabby things like that. And that's probably appropriate for ArrrrCamp. These are pirate procs. Okay, so here I have a higher order function called makeAdder. The reason it's a higher order function is that the thing it returns is itself a function. MakeAdder takes the number x and returns a new function that adds x to whatever value this new function gets as an argument. So I can use it, I can call makeAdder, give it a value 1, and this thing is going to return a function that adds 1 to an argument. In fact, I can take this, I can replace the definition of add1 with our new makeAdder call and run this, and we still see that we still get 33 out of the entire thing. So add1 still works, even though I'm creating the add1 function through the process of calling a higher order function. Let's do one more higher order function. I'm going to call it compose. It takes two functions, f and g, and it's going to return a function of a single argument that calls f on the result of calling g on the argument of that new function. So this takes two functions and calls them on top of each other, just like that. And let's compose mul3 and add1 together. And I'm going to put that in a mul3 add1 function. And let's now call our new composite, our composed function, on the argument 10, and we see that we get 33 out of the result. So still no change. Again, compose is a higher order function because it takes an argument that is a function. It also returns a value that is a function. That's all a higher order function is a function that either takes an argument that's a function or returns a value that is a function, or perhaps in the case of compose, does both. Alrighty, so higher order functions, we're not really used to seeing them in everyday Ruby life, but if you do a lot of functional programs, this is your bread and butter. You do this all the time. So we're going to use this a lot, and you might as well just get used to that for the moment here, for this demo. The next thing I want to talk about is functional refactorings. And just like in the object-oriented world, there are a number of refactorings like extract method or method object or things like that that we can do to your code. There are certain functional refactorings that we can do as well. The first one I'm going to use is called the tenant correspondence principle. Oops, there we go. And tenant says that I can take any expression, wrap it in a lambda, and call that lambda immediately, and there's no change in the result. So let's go down here. Let's focus on this n times 3 expression right here. I'm going to take n times 3. I'm going to wrap it in a lambda expression, just like that, or stabby procs. And then I call it immediately, and that does not change the result of that. And we can see that by evaluating our buffer and seeing we still get the value 33 out of it. In fact, I like tenant so much, I'm going to apply it right here. And I actually have an editor macro. These things are entirely mechanical. So I got some editor macros to apply some of these functional refactorings. So here, hit return, and I automatically have done tenant on that piece of code that I've highlighted. And that still returns 33, no difference. The next refactoring I want to talk about is called introduce binding. And introduce binding says that I can add an argument to a lambda. Here we're going to call it XYZ. And I can name that argument anything I want to, as long as that argument is not used anywhere within the lambda that's in scope there of that argument. So XYZ is not used anywhere here. And then I can initialize the value XYZ with any doggone value I want to. And when I run this code, it doesn't change a thing. So that's still the same value, 33. In fact, let's do it just to prove that. Let's do it here. XYZZY, and I'm going to actually put a string in there. And we see it doesn't change a thing. So introduce binding is a refactoring that does not change the effect. In fact, all these refactorings don't have any effect. The next one is called wrap function. And it's a little trickier because to wrap a function, I have to start with a function. So down here, I am returning a functional value right here. And wrap function says I can wrap this function with a lambda like that, give it an argument v, and then pass in and call the internal function with v, and that has no effect. Essentially what I'm doing is I'm saying I'm calling a function inside, and I'm just put it inside a function that calls it. So it's at one level of indirection is essentially all I'm doing it, and passing in v as a value all the way down means that there's no effect. And we can see that we still get the value 33 out of that. So that's called function wrapping. That only works when you're wrapping an actual function. The last refactoring we need to talk about is really simple. It's just called inline definition. And I can take the definition of any function here and stick that definition in for the name where it's called, and it has no effect. Still get a 33. Let's do that with compose as well. Let's take compose here. Take the definition, come down to where compose is called right here, and insert it in, and we still get 33. Oh, let's go wild with this one. There's add 1, and I'm going to stick it down here where add 1 is, and let's take multiply by 3. Oops, let's get the entire function there, and go down here to multiply by 3. Let's clean up these guys here. We don't need those anymore, and we see that we still get 33. One more time, just for kicks. Let's take the mul3 add 1 and replace it right here. Get rid of that. And run this, and we see that we have a really fancy lambda expression that does a lot of work just to calculate the number 33. This is why I said this is the worst Ruby code you'll probably ever see. Now, the key thing about this is that it looks exactly like lambda calculus. It's following the rules of lambda calculus in that the only way we're binding things to variables is through a function call. And so this is kind of the goal of what I want to get to demonstrate lambda calculus. All right, I think we have now enough background to get down to the meat of the demo. And now I want to talk about recursion. I'm going to demonstrate recursion by using the factorial function. Factorial, the mathematical definition of factorial says that if your input is 0, then the result of factorial is going to be 1. Otherwise, it's going to be n times the factorial of n minus 1. And I can prove that by calling factorial on 5, and we know the value should be 120, and indeed it is. So if lambda calculus is truly general and can calculate anything, it should be able to calculate the value of factorial. So let's demonstrate this. Let's put this in lambda calculus form by inlining the definition of factorial. I said inline is one of my refactorings that shouldn't change anything. And I run this, and I see that I have a problem. It says the method fact is not defined anywhere. And the problem is that when I inlined it, I removed the definition of fact, and that's no longer bound anywhere. So I cannot inline and a recursive function. And so recursion in general in lambda calculus is not really strictly allowed. So if that's the case, how can we use lambda calculus to actually calculate something like factorial? Let's see if we can get there. I can start by saying, well, let's suppose I have a function that takes factorial as an argument. And it's going to be a higher order function. We'll call it make factorial. And it's going to take factorial as an argument and then use it internally here just like this. And now this fact here will be bound to the fact up here. So it's no longer an unbound thing. Then all I have to do to make the factorial function is to call make fact and pass in the net definition of the factorial function. Yeah, okay, there's a problem here. What do I type in for those question marks? What definition of factorial can I use? So I can define factorial if I have factorial already defined. It's like a chicken and egg problem. Okay, I haven't quite solved this issue yet. Let's go and let's see if we can be a little less ambitious. Instead of insisting we have a complete true factorial function, let's make do with something called a partial function. Now, a partial function in this context means a function that's defined over a subset of the domain. So if I have a function that correctly calculates factorial for the values of 0 through 10, and I give it to this function called improver, improver is going to take that partial factorial function defined over 0 through 10 and give me back a function that has improved it by one step and will return a value, a factorial function that works for 0 through 11. And let's kind of prove that. So I'm going to create a function called f0 that's an improver over, and I'm going to create an error function just right here. Error is a function of one argument, and it's just going to fail. Should not be called. So if I improve the error function, which is defined over the empty set of the domain for factorial, I will get back a function that works and correctly calculates the factorial of 0. What did I do wrong? Oh, I left a 5 in here. I don't want to call the 5 there. Yes, f0 correctly calculates the factorial of 0. Let's see if it can calculate the factorial of 1. No, it does not. That's disappointing. Oh, wait. I can create a function that calculates the factorial of 1 by improving f of 0. Yes. But it does not work for factorial of 2. Oh, but wait. 1, call f2, and it correctly calculates the factorial of 2, but does not do the factorial of 3. Oh, but wait. Well, before I go any farther, let's just inline all these definitions here. All right, let's call this f of x. And let's take this improver and let's call it a bunch of times. And make sure we balance out the parentheses there. And f of x now does 3, it does 5, it does 10, it does 14, but it does not do 15. So I've made it clear that I can create a partial factorial function that will calculate up to any finite limit that I want to if I just call improver enough times. But I still don't have a true, honest-to-goodness factorial function. I don't know what I just did there. Okay. Whoa. That was really interesting. My mouse is moving. I'm not touching it at all. Look at that. Okay. I have no idea what's going on here, guys. My mouse is totally unusable. Ah. If I can get my mouse to move up there. Okay. Bluetooth? Unless there's something else. Okay. Okay, we'll continue on best we can here. I always say that live demos are the scariest thing you can do in a talk. Okay, so this is not going to work for us. I mean, this will get us halfway there, but it's not going to get us all the way there. So let's get rid of that. Let's think about this. So first thing let's do is put this into, let's take improver. Let's make it an argument to a function like this. And the function body is going to be something like that. And then we're going to pass in as a parameter to this function the improver definition right here. So here's the definition of improver. And we're going to put something right in here in this body. And we're going to call this fx just like that. Okay. So just demonstrate this still works. There's improver on improver.error. And that should give us something that works with 0, works with 1, should not work with 2. Okay, so that's so that gives us the same thing here. So let's do something really weird. Instead of calling improver over and over again and passing in an error function, let's pass in improver to improver. Now this is a little bit weird, and we'll see this actually works for f of 0 because we've taken something that does not work for factorial at all and improved it by one step. However, it does not work for factorial of 1. And in fact, the error we see is that it can't be coerced into a fixed num, and that's because right here, if we make note that we're actually passing in improver now into our improver function. And we're calling improver with a number. We know that improver does not take a number as an argument. Improver takes a function as an argument. Well, up here, don't use the mouse. Up here, we're passing an improver to itself. So let's do the same thing down here. And it's going to return a function that should be somewhat factorial-like. And let's see if this works. Oh, it works for factorial of 1. It works for factorial of 5. Works for factorial of 10. It'll work for the factorial of 100. In fact, I think I can go up to like even a factorial of 1,000 if I want to. Beyond that, I begin to get stack overflows, but that's not part of what we're trying to solve today. So let's keep it at factorial 5. And there we have it. Here is in fact, let's inline this. Let's take this and take this down here and replace the definition of f of x with that. And now I have a pure lambda function, pure lambda expression that calculates factorial completely, and it's the full factorial definition. So we proved that yes, we can actually do recursion using nothing but lambda calculus, and that was where we're trying to get to. I'm running out of time already, so I'm going to pick it up just a little bit here. I have two problems with this code. First of all, the name improver is wrong, because improver takes a partial definition, and we're passing improver to itself. So this isn't actually the improver function anymore at all. It's something I'm going to call the X function, because I have no better name for it. It is a weird function that swallows itself and generates a brand new, fully recursive function out of that. The definition of that boggles my mind. So we'll call it the X function, the mysterious, self-swallowing, fully recursive function. The second problem I have with this whole structure here is that it mixes the mechanics of recursion with the definition of factorial. If I were to write another recursive function, I'd have to reproduce all this X of X stuff, and that's unfortunate. So I would like to pull this out into two separate pieces, and let's just do that real quick. Maybe. There. So I would like to get this, first of all, I would like to get this X of X out of there. And we'll start by using the tenant refactoring, just like that. I'm going to break this up into separate lines. And then I'm going to introduce a binding called code, and I'm going to initialize it with the error function. And just to prove I haven't changed anything, we still get 120 out of this. That's just two refactorings applied, doesn't change a thing, and I still get the same thing out of it. Now what I would like to do is point out, so I can bind anything to code that I want to, and I'm passing an error. What I would really like to do is take this right here and bind it right there. The problem is it's not going to work. I get a stack level too deep. The reason is that if you look at the definition of X, I'm passing in itself, and one of the things it does in the body here is call itself recursively. Well, that was fine when I was doing it here because I was only calling it recursively if I needed to. Now I'm always calling it recursively, and that's going to blow up the stack. So to get around that, I'm actually going to introduce, or actually wrap a function around that. That's the function wrap refactoring. And by doing that, I see I fixed the problem. No more stack dump. Well, I can function wrap anything that returns a function, so let's do it in here as well. That's the function wrap refactoring. And we see it still works. And now I would like to point out that this value right here is the same value that we're initializing code to. So I can take this out and then replace this with code. And it still works. 120. Well, let's just rename code back to partial now. And you see that all of a sudden, out of nowhere, our factorial improver function has returned to us, exactly like we wrote it in the beginning. Now, it's still buried in the middle of everything, so I want to pull that out. And we'll do that by doing another tenant function, tenant refactoring, from here to there. Let's wrap that entire thing in the tenant refactoring. Fix up the indentation just a wee bit there. Okay. And let's introduce another binding. Code worked so well for me last time. Let's do that again. Oops. And we still get 120. And, okay, so I'm going to do this, since my thing is messing up, I'm going to skip a step, and okay. Maybe. All right. It's the pirate hat, I'm sure. I don't know what's going on. All right, so, okay, there. Well, I'm going to take this value right here. I'm going to replace it with code, and I'm going to put the the improver, the definition of improver right down here as an argument. So here is the argument to the function here that's calling code, and I'm going to show you it still works. And now, let's clean this up just a little bit here. I'm passing the improver definition in as an argument, so let's rename code to improver. There we go. And now, look at this. Here's all the mechanics of recursion, factored out into a couple of lines. Here are all the mechanics of calculating factorial in our improver definition, which was used before. In this line, we're actually calling it. And it still calculates 120. Let's pull this out into separate pieces. I'm going to call this piece y. I'm going to call this piece right here fact improver. Still calculates 120. So now we have all the pieces together. Here is the definition of factorial. Here is something called the Y-Combinator. Out of nowhere it has appeared. And here is this. Let's just do one more pull out here. This is actually kind of a reverse inline, right? Because I'm taking defining names and replacing the definitions with names. So still works. Okay, so here, let me ask you a question. If I take fact improver and give it the function fact, what do I get out of that? Very good. I get factorial out of it. I would say that fact is the fixed point of fact improver. So there we tie back to the idea of a fixed point. So the fixed point of an improver function is the general purpose recursion function. So actually, y calculates the fixed point of an improver function. So we can call y the fixed point combinator. It's also called the Y-Combinator. In fact, this particular version is called the applicative order Y-Combinator. And the reason it's applicative order, applicative, no R in there, spelling counts, is because we had to add this function wrap right there. If you remember that refactoring to prevent stack recursion. Applicative languages evaluate their functions before, evaluate the arguments before they call the functions. Ruby does that, Python does that, Java does that, most languages we use do that. Haskell is not applicative order. It's a lazy language. That's called a normal order language. So the normal order, there's a version of Y-Combinator for normal order languages as well, and it generally leaves off that function wrapping refactoring. If you look this up in Wikipedia, you will probably find it not quite like this. They will probably name the improver function f, because they really don't like, in math, they don't like descriptive names for some reason. And the other thing is that probably you will see it not in this form, but in another form that looks like this. If I take x of x, that's returning factorial, and if I run it through the improver function, that shouldn't change anything, and it doesn't. And then if I function wrap this part right here, call v inside the function, end the function, there, and then do this, indent it like this, we'll see a symmetrical version of the Y-Combinator. If you look up the Y-Combinator in a textbook, you'll probably see this symmetric form right there. That's the Y-Combinator. In essence, its only purpose is to provide recursion in a language like in a language like lambda calculus, which has no recursion built into it. Okay. I love playing around with the Y-Combinator. I actually started out to understand this function some time ago, and came up with these refactorings that did it. And to me, it's beautiful code, because you see very complex and interesting things fall out of the simplest of definitions. If you enjoyed this particular talk, go look at a talk called Programming with Nothing by Tom Stewart. He essentially writes the FizzBuzz program using nothing but procs. No strings, no numbers, no nothing. Nothing but procs. And thank you very much. I think I ran a little bit over. I hope you enjoyed it. Oh, excellent.
Nice beer that fits our conference is we're at. So
thank you.
so
Thank you.